Section 2 on system theory is for the biggest part a review of what you have learned in previous courses. So I will not go over all the slides and the pace will be generally high. Refer to the 2 courses that have taught you the basics, and these courses are Signals and Systems. This is a course that is also available online, and Fundamentals of Control Theory of my colleague David Rouchard. Well, we'll start this section 2 on system theory by this very important result that links the convolution integral and the Laplace transform. Before we go any further, we have to talk about the hypotheses that are underlying the systems that we consider. Well, this hypothesis is that the systems are linear time invariant. This means that, for instance, if the system is subjected to an input x1 of t, and this produces y1 of t, and that if it is subjected to x2 of t, and it produces y2 of t, then by linearity, if you subject the system to a linear combination of these two signals, so alpha x1 plus beta x2, where alpha and beta are some real constants, well, then the output will be alpha y1 of t plus beta y2 of t, right? This is expressing linearity. Time invariance is very simple to explain in words, assuming that the system is at rest. If you do the experiment today and you do the same experiment tomorrow, well, you can expect 2 times the same result, the same response, if the system is time invariant. Well, a first main result is the result of the convolution integral. If you're given the impulse response of the system, h of t, so this is the response to a Dirac impulse, and you're given the input signal to the system, then you can compute the output y of t, and it is simply the convolution of h of t and x of t, and this convolution can be written as follows. And this is again under the assumption that the system is linear time invariant. So we've just seen that if you know that the system is described by an impulse response h of t and that you're given an input signal, well, you can obtain the output of the signal as follows. And here basically you stay in the time domain. Another way to go is to use the Laplace transform, and we'll define the Laplace transform very soon. And what you obtain then is the Laplace transform of the impulse response, and this is the transfer function, and the Laplace transform of the input signal, right, x of s. And the neat thing about this, that is, if you go this way, well, you can very simply obtain the Laplace transform of the output by taking the product of the transfer function with the Laplace transform of the input, right? Since we are interested in the output signal, the only thing that you have to do is, of course, compute the inverse Laplace transform to obtain the output signal. Well, a first reason to go through the Laplace transform is that it simplifies very often the computation of the response of the system. A second advantage is that there is a nice frequency domain interpretation. Assume here that the input signal is the sine of omega t u of t. Then the response of the system to this input, and it's very important that you see that it is the steady state response. This means that all transients have disappeared. Is really h evaluated in j omega, and then you take the modulus times the sine plus a phase shift. So what you have here is the argument of h of j evaluated in j omega. So what this says is that the steady state response, the response that you have after all transients have disappeared, is a sine at the same frequency as the input sine, but it is amplified or attenuated, and this is here the module of the transfer function when s is evaluated at j omega, and it is also shifted. So there is a phase shift, and this phase shift is the argument of h of s when s is replaced by j omega, and this leads to the concept of a Bode diagram that we'll review later. Using the definition of the one-sided Laplace transform, you can construct a library of Laplace transforms, just as we did in the course of signals and systems. We're going to use this table extensively, so if necessary, review the course and see how you can re-obtain this library of Laplace transforms. I will just review the three most important Laplace transform. The Laplace transform of a Dirac impulse, which is 1 without restrictions on the region of conversion. So the region of conversion is the whole S-plane. The Laplace transform of the unit step, which is 1 over S, and the region of conversion is the open right half S-plane, so everything that is to the right of the pole at the origin. And then finally the Laplace transform of the real exponential that is given over here, and this Laplace transform is given over here. This is a very important one because a first order system will have an impulse response that is equal to this quantity over here, and this will be the transfer function of a first order system with time constant t and gain k. We'll come back to that later. Well, we have seen that the output, or the Laplace transform of the output, is h of s times x of s. So the transfer function h of s is the ratio of the Laplace transform of the output over the Laplace transform of the input, right? So very often I will now use the acronym P of s to tell you that it is the process that we are considering for control. In the previous slides and in previous courses, I have insisted on h of s to tell you that it is the Laplace transform of the impulse response. Well, this transfer function transfers the Laplace transform of the input to the Laplace transform of the output. Well, the transfer function really characterizes the system by means of its poles and zeros, and it is therefore a very important tool for analysis and synthesis, and you'll see that in the next section that is dedicated to process behavior. Well, two responses, of course, that will play a very important role are the impulse response of the system. So this is the response to a Dirac impulse given zero initial conditions. That is when the system is relaxed, and what you recognize over here is the impulse response of a first order system. And another response that is of course very important in this course is the step response. That is the response to a unit step, again given initial conditions that are 0, so assuming that the system is relaxed. And what you recognize over here is the step response of a first order system again. We've just considered the step response. In the next section, we'll consider the step responses of dynamic systems. A dynamic system is a system for which the output at time t depends on the input at time t, but also on the input before time t. Such a system has memory. When it is subjected to a step-like input, well, such a system will go through a transient phase and finally the output will settle out. This will be very different for a static system because the output at time t only depends on the input at time t. It reacts immediately. It does not have memory. So if you look at the step response, and more in particular if you look the transient of the step response, you can learn a lot about the dynamic system. The step response is kind of the signature of the system. So let us look at a few step responses. So this is here the input, and as we've shown before, for instance, the first order step response will look like this, right? So it takes some time before the output settles, but this is clearly the characteristic of a first order system. For instance, the step response of a second order system will look very different. You can see here that the slope at the start is different. Here you have a slope, and here this slope is 0. Step responses might look very different. Okay, so this is here the step response of a lead lag system. Okay, so you can see here that by looking at the step response, we can learn quite a lot about the dynamics of the system, and this is what we're going to explore in the next section. It is very important to realize that a rational function in S, so for example here in this case 1 over S, can either be the transform of a signal or a transfer function. Okay, well, if 1 over S is a Laplace transform of a signal, this means that xs is 1 over s, so that the original signal in the time domain is x of t is in step signal, a unit step signal. Well, 1 over s can also be the transfer function of the process, and in this case h of s is 1 over s, and this process is an integrating process. Why? Because h of t, the impulse response, is a unit step. So you put an impulse at the input and you have a unit step at the output. Okay, so the unit step is the integral of the impulse, the Dirac impulse. So indeed this process has integrating characteristics. What we can do is combine both, and before we do that we can have a look at a system that has integrating characteristics, and it's the relation from this control valve over here that will influence the input flow over here to the level in the tank. If at the input you put an impulse, a Dirac impulse, right, what you will see at the output, so this is time here and this is the level, well, you will see that the output will evolve as a unit step. you open the control valve for a very short period, what will happen is that the level will increase. So what we are doing over here is really saying, well, y of s is hs x of s. In this case, x of s is equal to 1, and h of s is equal to 1 of s. 1 over s, sorry. So you have here 1 over s, which means that if you do the inverse Laplace transform, you have that y of t is u of t. Now what we can do is combine things, right? And what we'll do is put at the input a unit step, right? So now x of s will be 1 of s, right? The transfer function is still the same, and what we'll have is y of s is h of s x of s. So in this case this will be 1 over s squared, right? And if you take the inverse Laplace transform, you'll have that the output, in this case the level, will be t u of t. So what we'll have is a response now that will look like this. So you'll have a level which is going to increase, which is normal because we'll have a constant input flow into the tank, which will result in a level that increases linearly. So you can see here that 1 over s can be the Laplace transform of a step input, or it can be the transfer function of a process, in this case an integrating process. The stability of a causal system, and we'll always consider causal systems, depends on the location of the poles. And if the poles are all strictly in the left half s-plane, well, the process is stable. So let us look at the s-plane. So this is the real part of s and the imaginary part of s. So a system with poles that are all to the left of the imaginary axis corresponds to a process that is stable, right? So what could happen is that you have a process P of s with poles that are to the left, but that you have, for instance, one pole at the origin, right? Or a pair of complex conjugate poles, right? And this type of system, and here again this is the Laplace plane, so you have imaginary part of s. Well, such a system is called marginally stable. Let us take an example that you know. Well, for instance, if P of s is this integrating system that we have considered previously, well, here we have one simple pole at the origin. Well, that system is marginally stable. As you can see, if you take the inverse Laplace transform, well, the impulse response that is associated is a step. Okay, so this is not converging to zero and it's not diverging. So this system is at the limit of stability, or it is marginally stable. If you have several poles at the origin, or multiple complex conjugate poles, or poles in the left half plane, then the system is unstable. Well, what we'll use very often is the initial value theorem, and then afterwards also the final value theorem. And the idea is that you can establish the initial value of y of t. This is the value of y of t in the neighborhood of 0 using the Laplace transform of y of t. So the assumptions are as follows. Y of t and its derivatives have Laplace transforms, and then you can obtain the initial value of y of t, or the value of y of t in the vicinity of 0, as follows. So you take the limit when s is tending to infinity of sy of s. Remember, of course, that when you take the limit here when t tends to 0, as you have a 1 over x relation between time and frequency, this will correspond to, in the frequency domain, to an s that tends to infinity. It is possible to do something very similar to establish the steady state value of y of t when t tends to infinity. So that's the value of y of t when all the transients have disappeared. For this you have to use the final value theorem, but this final value theorem, and this is why I'm underlying this, comes with an assumption, and this assumption is that the poles of sy of s are to the left of the j omega axis. If this is the case, you can use the final value theorem to obtain the steady state value of y of t, and you can obtain it by considering this limit when s tends to 0 of sy of s. You can see here again that this relation in 1 over x between time and frequency is used. Here t tends to infinity and here s tends to 0. So make sure that you apply this final value theorem correctly, because for instance, if you apply it to an unstable process to, for instance, determine the step response, you will draw the wrong conclusions. The initial and final value theorems will be used quite extensively in the next section on process behavior. What we'll do is use it for a given process P of s, and this process will be subjected to an input x of s. In practice, we'll consider only two inputs, an impulse, Dirac impulse, and a step input signal, so that x of s is either 1, this is the Laplace transform of an impulse, or 1 over s, and this is the Laplace transform of a unit step. We are interested in what happens at the origin, so we would like to have y at the origin, but we're also interested in the slope. Okay, so the derivative of y evaluated in t is equal to 0. We're also interested in the steady state response, right? So we can apply the initial value theorem to have an idea of the response at the origin, right? This is simply applying the initial value theorem and replace y of s by ps times xs, and this is how you obtain this expression over here. You have something very similar, of course, for the steady state value. This is really a straightforward application of the final value theorem. What is maybe a bit new is that you can also obtain information about the derivative of y at the origin, because this is here simply the Laplace transform of the derivative of y with respect to time, right? So if you apply the initial value theorem, well, this is what you obtain, and you see here that it involves the output at the origin that you've just computed also with the initial value theorem. If you now specialize these formulas to xs is equal to 1, the Laplace transform of an impulse, this is what you obtain. As you can see, x of s has been replaced by 1. If you now specialize the formula to x of s is equal to 1 of s, and this is the Laplace transform of the input step signal, this is what you obtain. You can see that x of s has been replaced by 1 over s, and this allows us to obtain information about the step response of this system p of s at the origin and in steady state. In this course we are going to use sampling, and of course therefore you have to know the sampling theorem and the associated Nyquist condition. So the idea is as follows: we have a signal f of t and its Fourier transform yields f of omega, and if you look at the amplitude spectrum you can see that this signal has a low pass spectrum of finite support. This is a so-called band limited signal. Above a certain frequency the frequency content is 0. Of course in practice you will always have a little frequency content, but we'll assume here that we have removed everything above omega max. This signal is sampled, so t is replaced by kts, and we obtain the sampled signal, and here we're using ideal sampling. And if you take the Fourier transform of this sampled signal, you obtain fs of omega, and this Fourier transform can be computed from the original Fourier transform as follows, right? And this is 1 over ts, the sum, where k ranges from minus infinity to infinity, of shifted versions of the original Fourier transform, okay? And they are shifted by omega s, or multiples of omega s, right? And if we now look at the amplitude spectrum of the sampled signal, this is what you obtain. And what has to be prevented is that these motifs here in blue, well, they overlap, because this is going to cause aliasing, right? So this point over here, omega s minus omega max, has therefore to be larger than omega max. And if you rewrite this, this leads to omega s, the sampling frequency, is higher than 2 times omega max. And usually this is written differently in terms of the Nyquist frequency, which is half the sampling frequency. So the Nyquist frequency is higher than omega max. So you can see here that in this case here the Nyquist condition is respected. You have to understand this slide, and you have to be able to apply it to the sampling of a sinusoidal type signal, so that you can compute at which frequency the sinusoidal signal will present itself as a low frequency alias when the Nyquist condition is not met. If necessary, you can review the course of signals and systems, and the video course is available online. When the Nyquist condition is not met, it is impossible to distinguish between a frequency omega and its aliases, omega plus k omega s. So typically a high frequency will present itself as an alias, a lower frequency, and there is a loss of information. When does this happen? Well, for instance, if the original signal that is sampled is not band limited, it has a spectrum of unlimited support, well, you'll have problems when you sample it, because the Nyquist condition can never be met, right? So what you have to do is to use a low pass anti-aliasing filter. So you'll have to use a filter that looks like this. So this is omega and this is the amplitude body diagram, right? So it will look like this, and you will have to give it a sufficient roll-off. If the roll-off is not sufficient, well, you'll have to put the frequency here, the cutoff frequency of the filter, a little bit earlier than the Nyquist frequency, so that you have a sufficient attenuation at the Nyquist frequency. If the signal is band limited, right, but the Nyquist condition is not respected, what you could do is, of course, increase the sampling frequency until it is satisfied. After sampling, we have to work with discrete time signals. So the system is now described by its impulse response h of k, a discrete time sequence, and k here is an integer. Similarly, the input signal is x of k. We can now compute the response of the system described by this impulse response subjected to the input signal x of k, and that's y of k. And again, it is the convolution of the impulse response and the input signal. But here now, this convolution is a convolution sum that is defined as follows. So we have a first method to compute the output signal. Well, what you could do is go to this other domain, and this other domain is now the Z domain. The Z transform will be presented just afterwards, but the Z transform is the Laplace transform of a sampled signal. So the Z transform of the impulse response results in the transfer function in the Z domain h of z, and the Z transform of the input signal is x of z. Well, the neat thing about convolution in the Z domain is that it's just multiplication. So the Z transform of the output signal can be obtained by multiplying the transfer function with the Z transform of the input signal, right? And now to compute y of k, it's just a matter of taking the inverse Z transform. Remember that a signal f of t can be sampled by multiplying it with the Dirac comb. And if you do this, well, you obtain the sampled signal, and this sampled signal is given over here. So if we take the Laplace transform of this sampled signal, right, this is what you obtain. By linearity, you have to take a sum of the function evaluated at the sampling instance times the Laplace transform of this delta here, and it's a family of shifted deltas, and by the Laplace transform of a delta, which is 1, and the time shifting property, you can rewrite it like this, right? And now it's just a matter of notation. It's a sum, and we'll write it like that, and then we'll define the Z variable, and this will lead to the Z transform. This one you can rewrite as E TSS minus K, right? And this is Z, right? So this is the sum on K, f of K, Z minus K, and this is the definition of the Z transform. But you can see that it's simply the Laplace transform of a sampled signal. Here you have the definition of the one-sided Z transform. It is a transform for causal signals, or for signals that haven't been made causal by multiplication with the unit step. So In the previous slide we had found this expression here, and here k ranges from 0 to infinity since we're working with a causal signal. Of course, there is also associated to this a region of convergence. Using this definition of the Z transform, you can construct a table of Z transforms. I'm not going to insist in this course because we'll not work with the Z transform that often. I can hear that some of you are happy, but if you insist, well, you can go and have a look at the course of signals and systems that is available online. We'll just need a little reminder of the time shifting property, but in the case with 0 initial conditions, right? So if the Z transform of the sequence f of k is f of z, well, then the Z transform of this time shifted sequence is z minus k0 f of z. So for instance, if you have a system with transfer function z minus 1, right, and you compute the response to an input signal x of k with associated Z transform x of z, well, the response is simply, as we have seen, h of z, x of z. In this case, h of z is z minus 1 x of z. So if you take the inverse Z transform, this is what you obtain. So you can see here that z minus 1 is really the unit delay operator. Of course, it's maybe necessary also to talk about stability in the Z domain. So for a causal system, the condition is saying really that the poles of the system need to be inside the unit circle. So for instance, this system is said to be asymptotically stable in the sense that its impulse response will converge to 0. If you have poles inside the unit circle, for instance like here, and you have one pole on the unit circle or a pair of complex conjugate poles on the unit circle, well, then the system is said to be marginally stable in the sense, well, that it will not converge to 0, and the associated impulse response will not converge to 0, and it will not diverge. It's at the limit of stability. If you have poles outside the unit circle or multiple poles on the unit circle, then the system is unstable.